runaway supermassive black hole. Yes, that's exactly what this is about. Astronomers have long suspected some black holes get kicked out of their galaxies, but confirming one has been close to impossible. So how did this one betray itself? Stay with me. We'll show the observation trail, why its motion can't be a normal jet or galaxy, and how a streak of newborn stars became the smoking gun. By the end, you'll see how galaxy mergers and gravitational recoil can literally fling a monster into intergalactic space. If gravity only pulls, what gives a black hole the shove to leave an entire galaxy behind? Start with the prediction that kept theorists busy for decades. When two supermassive black holes merge, they don't just settle quietly. If their spins and masses aren't perfectly balanced, the torrent of gravitational waves can shoot off unevenly, like a fire hose that kicks backward. That recoil should launch the merged black hole at hundreds to thousands of kilometers per second. The math said it could happen. Telescopes kept coming up empty when it came to a clear, visual case. Two roads might lead to the same exile. One is that gravitational wave recoil, born in the moment of merger. The other is a three-body slingshot during a messy galaxy collision. Picture a crowded nucleus where a third black hole barges in. Gravity trades energy chaotically, and one object gets flung out at high speed. Both pathways work on paper. Both are brutal to confirm, because the action is brief and the players turn dark fast. Think of two figure skaters locked arm to arm, spinning faster as they pull in their hands. Now one twist is off-center, and when they let go, one skater shoots away. That asymmetry is the key. In a black hole merger, if the spins tilt and the masses are close, the gravitational wave spray has a favored direction. Momentum has to balance, so the remnant jumps the other way. General relativity allows recoil velocities of thousands of kilometers per second when the conditions line up. How hard is it to escape a galaxy? In a big spiral or elliptical, the escape velocity near the core can push past 1,000 kilometers per second. It falls with distance, but a heavy weight still feels a deep potential well. So a black hole needs not only a strong kick, but the right angle through the least obstructed path. Speeds of a few thousand kilometers per second start to clear the system and head for intergalactic space. Now add the mass problem. Launching a star is one thing. It weighs a single sun. A central black hole can pack millions to billions of suns. Momentum, not speed alone, rules the outcome. The same velocity for a much heavier body means an enormous momentum that needs to come from somewhere. With gravitational waves, the momentum source is the radiation itself, stolen from the orbital energy and spin of the binary. In a three-body encounter, momentum trades among the black holes, often dumping one to freedom while the others stay bound. Simulations help set expectations. When two black holes have near equal masses, high spins, and spins tilted relative to the orbit, the recoil can climb to roughly 5,000 kilometers per second. Those are rare alignments, but not absurd. More modest configurations give a few hundred to a couple thousand. That's enough to reach the edges of many halos or slip out entirely if the path is clean. So if kicks are real and sometimes huge, where were the runaways? Most ejected black holes are dim. They don't glow without fuel. Even if some gas tags along, the bright phase might be short. And a naked black hole in intergalactic space has no disk to power a quasar beacon. Surveys are blind to objects that don't shout in light. The workaround is counterintuitive. Don't stare at the black hole. Look for what it does to its surroundings. A fast, compact engine plowing through diffuse gas drives a bow shock that compresses material just enough to spark star formation. Those newborn stars keep shining long after the engine moves on, laying down a long, thin chain that tracks the path like a fluorescent footprint. Find the line, date the stars along it, and you have a speedometer for something that isn't there anymore. So what kind of trail keeps its shape for 200,000 light years? And how do we rule out the usual suspects like jets, tidal debris, or chance alignments that only look straight from our angle? A razor-straight streak of newborn stars across intergalactic space. What engine lays down a line like that? Start with what the images show. Deep Hubble data catch a thin, linear plume leaving a compact galaxy core running out for about 200,000 light years. It keeps a steady width over most of its length and points almost perfectly away from the nucleus, like someone drew with a ruler. The upstream end sits right at the galaxy's center, while the far end flares into a compact, bright knot. That knot isn't a random smudge. It looks like a concentrated pocket of recent star formation, capped by richer gas at the leading edge. Now, the obvious suspects. Could it be a jet lighting up a trail of gas? Jets can run long distances and create bright knots. Or is it a tidal tail from a close galaxy encounter, the kind that stretches stars and gas into arcs? Another option is a coincidence. Several background galaxies lining up to fake a straight trail. Each explanation has a signature, and the details here push in one direction. Morphology gives the first clue. Tidal debris tends to curve, break into clumps, and fan out, because it traces orbits in a changing gravitational field. This structure stays narrow and remarkably straight for its full reach. It doesn't show the broad fans or S-shapes you expect after a major interaction. The far end knot looks like a bow-shaped cap, not a lobe or bubble. Its symmetry and the consistent width argue against a stitched-together background alignment, which would vary in thickness and color from galaxy to galaxy. Ages along the line add another layer. The stars near the far knot appear youngest, while stellar populations grow older as you step back toward the host. That gradient looks like a moving trigger pass through gas and left stars behind in sequence. Think of a snowplow shoving a ridge forward. The newest pile sits at the blade, older piles behind. Here the blade would be a compact engine at the leading edge that compresses gas as it moves, igniting star formation on the fly. Spectre back to sun. The trail lights up in strong H-alpha and O3, with line ratios that match classic H2 regions powered by hot, young stars. You don't see the hard, non-thermal fingerprints that jets imprint when they shock and ionize gas directly. Instead, the emission looks like normal, ongoing star birth, distributed along the path the way you'd expect if dense pockets kept getting squeezed past a threshold. Then there's motion. Velocities change along the streak in a way that tracks a fast-moving object cutting through a gaseous halo. The gradient isn't anchored at the galaxy like a stationary jet would be. It shifts along the trail, consistent with a source that traveled out and left a record of its speed and direction. The gas shows a bow-like signature at the head and calmer dispersions behind, lining up with a supersonic passage. Compare that with radio jets we've mapped. Jets make chains of bright knots and large lobes where energy dumps into the medium, often with sideways offsets, shocks, and backflows. What they do not produce is a clean, monotonic age sequence of stars that grow older with distance from the tip back to the core. Their ionization fields also skew hard, while this trail's spectra stay in the star-forming regime. Put the pieces together and the best fit engine is a runaway supermassive black hole hauling a small accretion disk and driving without shock. As it rams through the galaxy's halo, it squeezes patchy gas above the collapse threshold and leaves a glowing wake of newborn clusters. The bright cap marks where the compression is strongest right now. If this is the path of an ejected giant, the next question is what that single detection tells us about how galaxies build their centers and how violent mergers shape the universe. One runaway black hole with a starlit wake turns a math-heavy prediction into a working probe. That line of newborn clusters maps where gravity is deepest and where gas hides in a halo you can't see otherwise. You can treat each trail as a ruler and a stopwatch. Now watch the hunt scale up. Hubble can spot the geometry. JWST can date the stars and weigh the dust. Wide surveys can catch fresh streaks in bulk. Each detection narrows merger models and tunes gravitational wave forecasts. If one escaped, how many roam the dark between galaxies? And how many quiet galaxies already lost their hearts? Thanks for watching.